Okay, hi everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Esperet from Grenoble, who's going to be talking about packing and covering balls in planar graphs. Go ahead, Louis.
Okay, thank you very much, and thank you for the invitation. I'm going to talk about some project that we did with several other people: Nicolas Bousquet, Wouter Kams from Battenburg, Gwenaëlle Joret, William Lochet, Carole Muller, and François Pirot. So a lot of people. So before I talked about specifically about balls in planar graphs, let me talk about packing and covering in general. So when you have a hypergraph, there are two very nice and important natural parameters, which are on nu and tau. So nu, it's a packing number or the matching number. This is the maximum number of vertex disjoint hyperedges in your hypergraph. So that's nu, and tau, the transversal number, is the minimum number of vertices that you need to hit all hyperedges of your hypergraph. So the minimum number of vertices in a set S, such that each hyperedge contains an element of S. Okay, so this is nu and tau, the matching or packing number. I'll always talk about packing and the transversal number of the hitting set. So I'll talk about packing and transversal. And these two are related because if you have k vertex disjoint edges in your hypergraph, you'll need at least k vertices to hit all hyperedges. So tau is always at least nu. But you have actually more than that. If you know linear programming, you know that these two parameters are dual. And so the fractional relaxation of the two parameters, which are denoted by nu star and tau star, are actually equal. And they are coined between nu and tau. Now I'll go back to linear programming and fractional relaxation later in the talk. So I'm not going to define these now, but we have this nice chain of inequality. And in combinatorial optimization, like the natural question is, can you say more about tau and nu? So there are a bunch of typical questions that people ask in this context. So when do you have tau equals to nu? So that's the first question. Usually when you have this, it's a nice min-max theorem, like Koenig's theorem, that maximum size of a matching is the minimum size of a vertex covering bipartite graphs. It's exactly a tau equals nu theorem. When you don't have this, you might be happy with something a bit weaker, but just is tau bounded by a function of nu? And then you're talking about a class of hypergraph, of course, not just a single hypergraph. And when you have this, it's called usually it's called Erdős-Pósa property. And originally, Erdős and Pósa, they were interested in cycles in graphs. And the natural hypergraph here would be all the cycles of a graph. This is tau bounded by a function of nu. And if you have this, sometimes you might be even happier if you have a stronger relationship between tau and nu. And one such example is when tau is bounded by a constant times nu. Usually you said that the duality gap is bounded. And this is very useful in algorithmic design, having this relationship. And sometimes you're not that lucky, but you can be still happy if tau is close to tau star or nu star is close to nu. And then you talk about the integrality gap. Okay, all these things are very classical in combinatorial optimization. And you're really happy when you have these for either for structural properties or for algorithmic design. So you're really happy when you have these. And the natural question is, like, in which situation you have these properties. All right. So okay, a natural question is when you don't have these properties. So let us see just a very simple example of when tau is not bounded by a function of nu, and it will be helpful in the remainder. So let's see a nice example. So you take a complete graph on n vertices, and you look at the dual hypergraph. Okay, so we take complete graph here on 4 vertices. And what is a dual hypergraph? The vertices of this hypergraph are the edges of Kn. So here we have 6 edges. So we have 6 vertices in our dual. And we have n vertices. So n is 4 here. We have 4 vertices in K4. And this corresponds to edges in the dual. Okay. So we have 4 hyperedges, and each hyperedge corresponds to a vertex. So here, this vertex has 3 incident edges, and thus these 3 vertices form a hyperedge. Okay. So K4 has 4 vertices and 6 edges. So the dual has 4 hyperedges and 6 vertices. And you can ask what tau and nu are. And well, if you take any 2 hyperedges, they would correspond to vertices of Kn. And these 2 vertices, they have a common edge. And this common edge must be some vertex that is in the intersection of the 2 hyperedges. Okay, if you look at the green hyperedge and the red hyperedge, they have a common vertex here. So nu is equal to 1. You can't find 2 vertex disjoint hyperedges here. So nu is bounded by a constant 1, but still tau is very large. And the reason is that each vertex of your dual intersects just 2 hyperedges, the 2 hyperedges corresponding to the 2 endpoints of the edge. So if each time you hit, like you take 1 vertex in your transversal, you're only hitting 2 hyperedges. But your hypergraph has n hyperedges. So you need at least n over 2 vertices if you want a transversal of your hypergraph, right? And actually, you can do that with n over or close to n over 2 because you just take a matching in your clique, the maximal matching. So n over 2 is roughly the right answer. But you clearly see that nu is not related to tau. Like nu is 1, and tau can be very large. So here you don't have tau, which is bounded by a function of nu. So this is a very simple example, but what's really nice here is that it's when you don't have this kind of structure in your graph, you're happy. And this was proved by Ding, Seymour, and Winkler in '94. If you don't contain a copy of this bad example, say K star D, the dual of KD for some fixed D, then tau is bounded by a function of nu in your hypergraph. And it's nice because it's even a polynomial in nu. And the exponent of the polynomial only depends on 2D plus 3. Okay, so this is a bad example, but if you don't have this bad example, you're happy. And it's really nice. All right, so this was some general introduction about packing and covering. There is much more to say, of course. From now on, I'm going to specialize to a specific type of hypergraphs that is very natural in geometric graph theory. These are ball hypergraphs. And yeah, we're going to specialize these packing and covering questions to balls in graphs. So what is a ball? So the R ball, or the ball of radius R, is the set of all vertices at distance at most R from a vertex V. This is denoted by BRV. And when you fix R, you have a natural hypergraph defined by all the balls. We call it BR of G. The vertex set is all the vertices of G, and each ball is a hyperedge. So all the hyperedges are all the balls in your graph. So you have as many balls as vertices. So BR of G is a very nice hypergraph. It's a very the very nice property is that it's self-dual, right? Because U is in the ball of radius R centered in V, if and only if V is in the ball of radius R centered in U. So it's a very nice and natural class of self-dual hypergraphs. It's quite cute. And what are tau and nu of these graphs? So first, nu. So from now on, we fix some integer R, and nu of this hypergraph of balls of radius R. What is it? So by definition, it's the maximum number of vertex disjoint R balls in G, and 2 balls centered in U and V of radius R of vertex disjoint if and only if the distance between U and V is at least 2R plus 1, right? Then the two balls are disjoint. So saying that you're taking vertex disjoint balls of radius R is the same as saying that you're taking an independent set in the graph to the power 2R. Okay, what's G to the power 2R? It's G, and you add vertices, or you add edges between vertices at distance at most 2R. Okay, so packing balls of radius R is exactly the same as finding an independent set, a large independent set in the graph to the power 2R. So it's quite natural parameter here. So this is new, and I'm going to denote this by new R of G because otherwise it's a bit cumbersome. So what is tau now? Well, tau is also quite natural. So it's, by definition, it's the minimum number of vertices you need to hit all R balls in the graph. But if you view this, I mean, it's exactly the same as the minimum dominating set in G to the R. Because if you hit all balls of radius R, it means that every vertex is a distance at most R from one of the centers that you selected. So it's exactly a dominating set in G to the R. So these two parameters, tau and nu, they have a very nice and natural and graph theoretic interpretation for ball hypergraphs. And actually this problem of packing and covering has been considered directly with, I mean, I'll go back to that, but yeah. So this has a natural interpretation into graph problems. And so we still have this chain of inequalities. Nu is at most the fractional relaxations, which is at most tau. And is there a connection between tau and nu in the other direction? And the conjecture here, which was made by Chepoy, Estelon, and Vaxas in 2007, states that when G is planar for any R, tau is bounded by an absolute constant times nu, and furthermore, the constant doesn't depend on R. Okay, so the conjecture is that the duality gap is bounded independently of R. Well, let me, I'll give some, I mean, some results motivating why this conjecture should be true, but maybe the first motivation should be completely geometric. So this problem of ball hypergraphs, you can define it in graphs, but you can define it in any metric space. To define a ball, you only need the notion of point and the notion of distance. So you can ask the same question in any metric space, not just in a graph. And the natural metric space that looks like planar graphs, but is much more simple, is the plane. What about asking this question in the plane? So let me jump to make some picture. So is it true that in the plane, tau is bounded by a constant times nu that doesn't depend on R? So you have R balls. So these should be all of the same radius. So you have R balls in the plane. And is it true that tau R is at most a constant times nu R? So in the plane is invariant under rescaling. So if you scale the plane by a factor of R, you don't change anything. So actually you can assume that R is equal to 1. And clearly, like everything, nothing should depend on R. Okay, if you prove a bound for R equals 1, it will also prove it for any R. So in the plane, clearly, if you prove something, some relation between tau and nu, it will be it won't depend on R. But is there a relation like this between tau and nu in the plane? And the answer is yes, and it's quite easy to see. So the idea is that you take any set of points, you look at the corresponding balls, and what you do is you take a maximum packing. So you take a maximum packing, so the balls are of disjoint. And it's maximum packing, so of radius 1, because I took R equals 1. And now it's maximum, so each point has to be a distance at most 2 from one of these balls. Why? Because if it was a distance more than 2 from each of these balls, then the corresponding ball would be disjoint from everything, and it would contradict the fact that it's a maximum. Okay, so each point has to be close from one of these balls. So each point lies in the ball of radius 2 centered in one of these points. But now I claim that if I look at such a ball of radius 2 and such a ball of radius 1, so this is a ball of radius 2, and now I think what we discovered is that all the points are in such balls of radius 2 centered on these points. And the natural thing is that a ball of radius 2, you can partition it into a constant number of regions of diameter at most 1. So you have a constant number of regions here of diameter at most 1 that cover this object. Constant is, I don't know, maybe 18 or something like this. And what you do is you look at all these regions that have small diameter, and you pick one point in each of these regions, if this region is not empty. And I claim that now you have a heating set for all the balls that intersect this ball. And this is because the center has to be there, and each of these regions has diameter at most 1. So each point has to be at most 1 from one of these points. So you have at least 18 points per ball. So you find that tau is at most 18 times nu. And the only thing that you have been using is that you can cover a ball of radius 2 with a constant number of regions of diameter at most 1. And you can recheck that, like maybe 18 or 19 or 20, but some constant. Okay. So in the plane, it's true, and things don't depend on R. So maybe if we're happy, the same should be true in any planar graph. Planar graphs are a bit more complicated than the Euclidean plane. Like the right analogy would be the plane is the same as a grid in the metric sense. But planar graphs can be much more wild, and it's not clear that this conjecture should be true. But this was one of the motivations. All right, so what's known about this conjecture? So two main results. First, it's known that tau and nu are related by a function that doesn't depend on R. Just tau is at most nu to some constant c. And the reason of this is exactly what we have seen. It's a simple consequence of the result of Ding, Simu, and Winkler. Remember what we have seen earlier? This theorem tells that if you don't contain a copy of the dual of KD, then tau is bounded by a polynomial in nu. So we only have to prove that in a ball hypergraph, we don't have a copy of the dual of a large clique. So what would be the dual of a large clique? It would be a certain number of balls, d balls, and for any two balls, there's a vertex in our graph that only lies in these two balls. Okay, this is exactly the dual of a clique. And using the fact that these are balls and not just any set, you can actually prove that if you have such a copy of such thing in your ball hypergraph or in your system of balls, then you have KD as a minor. The way you do that is just you take the shortest path tree between each center on each leaves here, and using the fact that these are balls and some careful analysis, you find a KD minor. Okay, but it's really it doesn't seem so. It seems that we could only use the fact that that balls are connected. We could only use it. But if you replace balls by connected subgraphs, it's completely wrong. You can't prove this. Okay, so balls are really important here. Okay, and actually the result here is a bit more general than that, and it will be useful later. If you take any system of balls like this, and for every pair of intersecting balls, they have a private vertex that is only contained in these two balls, then the intersection graph of the balls appears as a minor in your original graph. you don't need that this is a clique or something like this. You will really find the intersection graph of the balls as a minor in your graph. Okay, that's quite useful. And again, really, balls are necessary here. All right, so this is one first. If you want to convince yourself that the conjecture is true, at least you should be able to relate tau and nu in a way that doesn't involve R, and this is the case by this result. And the second result that actually tells you, okay, this conjecture should be true, is a result of Zdeniek-Dvořák, which is earlier than this. And Zdeniek proved that tau is bounded by a constant time nu, but the constant actually depends on R. And so the strength of this result is that this holds not only in planar graphs, but in any class of bounded expansion. This is very broad. I'm not going to talk too much about bounded expansion, but it includes minor classes that are closed under topological minors, classes of graphs that have a low dimensional representation as intersection graphs. And so it's very broad and the result is very strong, but actually somehow it's a bit too strong because I will talk about it later. We don't expect that in such generality, we can prove the same result with a constant that doesn't depend on R. But anyway, at this point, tau is at most a constant that depends on R times nu. And also tau is bounded by a function of nu that doesn't depend on R. So when you see these two results, I mean, the first reaction, okay, the conjecture has to be true. It's not possible. It should be true. But so actually, we proved that it's true, but it really took us many years to convince us to find a proof that this was true. Even if with these two results, it's amazing that it should be true. All right. So what did we prove? So two results. First, the integrality gap between mu star and nu is bounded by a very small constant, actually something like less than 18. And the proof is very short and simple. I'll give you the proof in a minute. And this, by known result, it directly implies that tau is bounded by nu log nu with a small multiplicative constant. So you get almost linear bound that with a constant that doesn't depend on R, almost for free from this result. But then you can even get the right conjecture. Tau is bounded by a constant time nu with a constant that doesn't depend on R. And here the constant is much larger, unfortunately. And the nice thing is that this result is not just for planar graphs, but it holds for any minor closed classes. And as you would expect, the C would depend on the minor that you exclude. And the second nice thing, and somehow it explains why things shouldn't depend on R at all, it holds for any system of balls in your graph. So you take balls of different radii, and you look at the packing and the covering, and the packing, or the transversal is at most a constant and the packing in this system of balls, even if the balls are completely different radii. So it feels that nothing should depend on the radii of the balls. It's not even, you don't even have to take balls of the same radius. You can take balls of any radii, and this works. But somehow this explains why you shouldn't expect things to depend on the radius. But interestingly, if you try to prove this in the plane, that if you take any set of balls of possibly different radii, and you look at the corresponding hypergraph, prove that tau is at most a constant and nu, that's not easy. And I don't have a nice proof of that apart from using the same machinery as we do. Maybe there's a nice argument, but I don't have it. All right. So let me maybe give you some hints or some intuition on why all of this holds. But before that, maybe if anyone has a question or if you need some precision, don't hesitate to interrupt me. Okay. So we're going to prove or to see arguments for these two results, actually everything is quite simple. But the first result is I'm going to show you a proof, which is nice because it's applicable in a larger setting. I mean, you can reuse the same idea to prove other results rating the fractional packing and the packing. So it's really nice to see this argument. All right, so let me say what this new star is if you don't know the fractional relaxation. So there are many different versions. You can write things as linear programs, but I'm not going to use that. So let us define new star as the supremum of all fractions p over q, such that you can find p balls. I'm only going to talk about r balls during the talk for simplicity. So R is fixed. You're going to find p balls in your graph, possibly with repetition. So you can take the same ball several times. And each vertex lies in at most q of these balls. Okay? So if you take q equals 1, get exactly a packing, because each vertex lies in at most one ball. But now you're allowed to take q larger and p larger, and what you do is you optimize over all fractions p over q. So this is new star, and clearly it's at least new. And tau star, it's the infimum of all fractions p over q, so that you can find p vertices, again, possibly with repetition, and each r ball contains at least q of these vertices. And once again, if you take q equals 1, what you're talking about is really a transversal. Each ball contains at least one of these vertices. But now you optimize for p over q, and you have something that's most tau. Right? This is the fractional relaxation, and this the supremum and this infimum, they are a max and a mean. This is what the LP duality tells you, and LP duality tells you this same sequence of equations that tau star is equal to nu star, and this parameter is coined between tau and nu. Okay, and what we're going to prove now is that nu star is, for planar graphs, nu star is at most 6e times nu, and e is Euler's constant. Okay, and the proof is quite short and elegant. Okay, so let us see how to prove that. I jump to the whiteboard. Okay. All right. So we have nu star, which is equal to p over q for some p and q, and it means that we have a certain number of balls. We have p balls, and each vertex lies in at most q balls. This is really the definition of nu star equals p over q, right? This is the definition. So what we want to do is we want to find a large, we want to prove that the packing is large compared to nu star. Okay, so again, we want to prove that nu star is at most 6e nu. Okay, the goal is nu star is at most 6e nu. If I rewrite it, I want to prove that nu is quite large, 1 over 6e times nu star. Okay, this is really what we want to show. So we have a large fractional packing, and we want to extract a large packing. This is exactly what we want to prove. And the way we're going to do that is by defining H as the intersection graph of the balls. So you have one vertex for each balls, and two vertices are adjacent if the balls intersect. And what we want to prove is that alpha of H is at least 1 over 6e times nu star. Okay, because alpha of H, it's an independent set in the intersection graph. So it's exactly a number of vertex disjoint balls. Okay, nu is exactly an independent set in this intersection graph. Do we agree? Okay, we have a fractional packing. So we make an intersection graph out of it. And we want to extract a packing, but packing is actually an independent set in this graph. Okay. So one way to prove that the independent set of a graph is large is to prove that this graph has small average degree. So our intermediate goal will be to prove that the average degree of H is at most 6EQ. Why are we done if we prove this? Well, you know that if you have a graph on n vertices and that has average degree at most d, then it has an independent set of size at least n divided by d. So it's a general result. Alpha of H is at least the number of vertices of H divided by the average degree of H plus 1. It's a classical result. You take a random order on the vertices and build the greedy independent set. And you can prove that the greedy independent set has size at least number of vertices divided by the average degree plus 1. Okay. And well, average degree will be quite large. So this is not very far from number of vertices divided by average degree. What is the number of vertices of this graph? Well, we have p balls. So the number of vertices is p. And the average degree, it will be at least 6EQ. So this is 6EQ. So this is 1 over 6E times P over Q. And this is exactly 1 over 6E times nu star. Okay, so this is nu. And we have that nu is at least 1 over 6E times nu star. And this is exactly what we wanted. Okay. So the only thing we have to prove is that our graph has a very small average degree, 6EQ. Okay, we agree on that? So how can we prove that the average degree of our intersection graph is small? So we would be very happy if Q was 2. So why is it the case? So we have our balls and say we have Q equals 2. So vertices are in at most 2 balls. Why are we happy in this case? Well, we have seen this proof that when we have balls like this, and we have some private vertex that is only in these 2 balls, we will be able to extract a minor. If we extract a minor, this minor would have very small average degree, and because it's a minor of a planar graph, it will have a small average degree. So we would be very happy if Q was 2, but Q can be very large. So how can we reduce the case that Q is large to Q equals 2? So how do we reduce a packing where each vertex is not most Q balls to a packing where each vertex is not most 2 balls? And the idea is simply to select the balls at random. So we are our intersection graph H of the balls. We are going to define a random subgraph H prime in the following way. So we take each ball with probability 1 over Q. And we're not going to keep all edges. We're only going to do the following. So for each ball, originally I keep, so this is the ball of U and the ball of V. For each ball, U and V, I'm keeping some vertex XUV that is in the intersection. It can be, the same vertex can be taken for many different balls. It doesn't matter. Okay, so I take, in my subgraph, I take each ball with small probability, just 1 over Q. And now I keep each edge. So we keep U, the edge UV in H prime. If U and V were both selected by our random choice. And this vertex XUV is now only contained in the ball of U and the ball of V. Okay. Okay, so let me tell again what I'm doing. So H is the intersection graph of all the balls. So I have P balls and each vertex is in at most Q ball. And I want to make this nicer. So I'm only selecting each ball with small probability, 1 over Q. And I want my graph to be very clean. So what I'm doing is I'm only keeping an edge between U and V if this point here in the intersection that I selected in an arbitrary way beforehand now is only in the ball of U and the ball of V. So all the other balls that maybe contain this point, they have disappeared. I didn't take them by my random process. Okay, so I have my graph H, and this defines a new graph H prime. So what can I say about H prime? All right, so let's say this is H prime. I'm interested in the number of vertices, the number of edges, and the average degree. So how do these parameters change from H to H prime? So I'm taking each vertex with probability 1 over Q. So in expectation, the number of vertices will be divided by Q. Okay, so the number of vertices of H was P, and now it's P over Q in expectation. What about the number of edges? Okay, so I remember I kept an edge between U and V if both U and V were selected. And this happens with probability 1 over Q square. Okay, U is selected with probability 1 over Q, and V is selected with probability 1 over Q. So it's 1 over Q square. And all the other balls that contain XUV disappeared. Okay, but you only had at most Q minus 2 such balls. So this happens with probability at least 1 minus 1 over Q to the Q minus 2. And this is at least 1 over E. Okay, so the number of edges, so let's call it M. Now it has been divided. It's at least M divided by EQ square. Okay, it has been divided by something, but not too much. We kept a graph that is much nicer now, but that still has a lot of edges. So the average degree is the ratio between these two things. So sorry, M divided by P. And this was divided by Q, and this was divided by EQ square. So let's call it D. Now we have D to the EQ. Okay, the number of vertices was divided by Q, and the number of edges was divided by EQ square. So the average degree was divided by EQ. All right. So, but now my new graph H prime, why is it nice? It has a lot of edges, and each edge corresponds to 2 balls and a vertex that lies only in these 2 balls. But by the same argument, I know that H prime is a minor of G. Okay, this is the argument where I grow some tree centered in each center. So this is a minor of G, and G is planar. So the average degree here is at most 6, because a planar graph has average degree at most 6. So this proves that the average degree, the original average degree is at most 6 EQ. And this is exactly what we wanted to prove. Okay. Okay, so just to tell again what I did, I started with a fractional packing, and I wanted to extract a packing out of it. And for this, the only thing I needed to prove is that the independent set was large. Or if I put it the other way around, I wanted to prove that the average degree was small. But the average degree is too complicated to compute. So I make my graph nicer by selecting each ball with a small probability. And when I look at the graph that remains, it's much nicer, but it still has a lot of edges. And much nicer means that it's a minor of my original graph. And just using this, I know that the average degree of this thing is small. So the original average degree was small too. And so it had a large independent set. Okay. So the reason why I'm showing you this proof, which might be a bit technical, is that it's actually useful not just in this setting. With the same argument, you can prove the best known bounds relating new and new star for other parameters, like directed cycles in planar digraphs, for instance. All right. So this proves this bound, and actually 6e is not so large. It's something that maybe less than 16 or something like this. So it's a reasonable bound relating new star and new. And as I told earlier, using this another known result, you directly have a bound like tau is at most new log new star, new log new. Sorry. But this doesn't quite prove the conjecture that we wanted. We wanted to have a linear relation between tau and nu. How do you prove this? Well, here I'm just going to sketch the arguments, but it's actually not that difficult in the end. Sorry. All right. So this is what we want to prove. Tau is at most a constant times nu, and the constant doesn't depend on R. So the general sketch of the proof is that you just start with a maximum packing, a bit like in the Euclidean plane. And you divide the remaining balls into two sets. So those who intersect few balls of the packing and those who intersect many balls of the packing. And few and many is just at most some constant or more than some constant. So what do you do about the balls that intersect few balls of the packing? So what you can prove, and it's not obvious, but you can prove that you only have a linear number of possible traces. So a trace would be the set of balls of the packing that some ball intersects. That's a trace. And you only have a linear number of traces of size at most L. And the constant will depend on L, of course. Right? It's not so easy to prove, but you can prove that. So you only have a linear number of possible traces. And for each such trace, so for each subset of L balls of the packing, if you take a packing of the balls that intersect precisely the subset, this is bounded. And the reason is that, let me jump again here. So we take a, so we take our packing, and now you fix these balls, and you look at all the balls that intersect precisely these four balls. And you look at the packing here. And I claim that the packing here is small. So if I take L balls, the packing here is at most L plus 1, or at most L, sorry. And the reason is that if I was able to pack more than L balls here, I could replace these balls by my packing here, and I would have a larger packing. Okay, because these balls, they intersect only these L balls. So if I have a large packing, I can forget about these balls and take these ones instead. Okay, so the packing here is bounded by L, actually not L plus 1. So the packing is bounded, but we know that balls, they have this nice Erdős-Poscher property. So the transversal is also bounded. So you have a linear number of different traces, and for each of them, you have a transversal of bounded size. So you have just a constant times b, a transversal of type constant times b that intersect all the such balls, the balls that intersect few balls of the packing. All right, now we only need to consider balls that intersect many balls of the packing at more than L. And again, here you can argue that the packing number of this is small, and this is for a slightly different reason. Okay, I'm already at the end of my board. So we have our packing, and now we look at the remaining balls and assume that you have a very large packing of balls that intersect many balls. They would intersect many balls. So we have a bipartite, the intersection graph is a bipartite graph. And we can prove that this bipartite graph is a minor of the original graph. So, but this minor must have small average degree, but this shows that the average degree has to be quite large. So this forces the packing to be quite small. So the packing number is at most b divided by 2, and if you apply induction, you have a transversal for all these balls that has size half of this bound. And combining these two things, you have a packing of linear size. All right, I'm sorry if this goes a bit fast, but I'm just saying the intuition. You start by finding a transversal for balls who intersect few balls of the packing, and then you try to intersect balls that intersect many balls of the packing, and here you apply induction. And actually, at the end, just maybe a 1.5 page proof. All right, so this was the proof of the main result. We thought it would be much harder, and in the end, it was a bit disappointing that it took us so long. I had been looking at this problem for maybe 8 years or something. So, all right, so but still there are many interesting questions remaining. So let me talk about that. So we actually proved that tau is at most the content times nu for all proper minor closed classes. And the natural question is, can you go beyond minor closed classes? And actually, it turns out that you can't go much more beyond that. And even for subgraphs of the two-dimensional grids with all diagonals, you don't have this property that tau is bounded by constant times nu. So these are classes of bounded expansion. So from the result of Zdeniak-Dvorak, we have that tau is bounded by a constant depending on r times nu r, but we can't get rid of this dependence between the constants and r already for two-dimensional grids with diagonals. So classes that satisfy this nice property, they somehow, you're stuck between minor closed classes and subgraphs of the two-dimensional grid with all diagonals. There's not much space, but maybe like my intuition would be that the real answer is exactly minor closed classes. So if you take a monotone class and ask that tau is at most c times nu r for all hypergraphs, I believe that this is exactly minor closed classes. So you must exclude some minor, but I don't know how to prove that. So as I told at the beginning, this problem of packing and covering balls, you can define that in hypergraphs, in graphs, sorry, but you can actually define that in any metric space. So we saw an example in the Euclidean plane. And then the natural question is which nice metric spaces have this packing covering relation between tau and nu and something that would be linear. And we know that graphs and surfaces that exclude some minor. So they have this relation where the constant would only depend on the genus. And what I'm wondering is whether you can prove the same for any Riemannian surface. So a Riemannian surface is just a surface equipped with a nice metric. It's a continuous world. So now we're not in a discrete world anymore, but you take your continuous surface and you pick a system of balls, finite system of balls on the surface. And you want, this defines a hypergraph if you want, so points and balls. It's just a finite hypergraph. Is it true that this hypergraph tau is bounded by constant times nu, and c only depends on the genus of the surface? And this I don't know. I don't know how to prove that. You could think that you can approximate Riemannian surfaces with graphs, but it doesn't preserve exactly distances. So you have some loss, and so all our arguments that don't really apply here. So I think it's a nice question. It goes beyond graphs a little bit, but maybe the techniques might be helpful there. Okay, so I'm done. So thank you very much for your attention.
Excellent. Thank you so much, Louis. Let's do a round of applause if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. And does anyone have any questions?
Yeah, so I guess the obvious, well, I don't know, the natural question to me is, I assume that you can get something like tau r is at most nu r to the 1 plus epsilon for classes that are nowhere dense.
It's obvious to you, but I haven't thought about it at all. So no, but it's a really nice question. I'm not even sure that's true, but that's a very natural. Now that you say it, it's very natural. But no, it's actually a very good question. I haven't thought about it at all, but it's quite nice.
Okay.
So we somehow discovered at the very end that we couldn't go beyond minor closed classes with this example subgraph of the grid, but we haven't thought about making the relation slightly weaker than linear. But it's quite reasonable.
That this seems to to me your argument about new and the linear programming relaxation seems to me to show that like if you have bipartite graphs of linear neighborhood complexity, it seems to me like that works. I think that this is something that's known using a different approach, which is much more complicated than this. But I don't know, do you know if that's true as well? Like if this just bit about
so yeah, even just the version between new and new star, it's not clear whether yeah. So I think that I had to check the construction. I think that this also shows that new and new star were quite far apart. So for subgraph of the grid, so this asks this integrity gap questions already. Yeah.
Okay.
But I don't want to say. I have to.
Yeah. No. Thank you.
But actually, these are very good questions.
It's really pretty proof. Thanks.
But it's a bit strange because it seems that there's not much space between minor closed classes and these subgraphs of the two-dimensional grid with diagonals. But still, there can be something between, but I don't know exactly what it should be.
Right. Are there any other questions? Give people a second to think about it. All right, well, maybe I'll end the recording there. Thanks again, Louis, and we can keep chatting after that.